Good day, everybody. The last webinar was a bit general, the one about the Python tools, Mike.io, Mike.io 1D, Mike plus Pi. Today, this is really only about water distribution. Our auto-calibration for collection systems is growing, but at the moment still very specific for only one catchment. So there is still a bit of work ahead. But auto-calibration for water distribution systems is quite powerful already. I hope you join my view. You agree? Let's start with a few very practical aspects for today's webinar. So I'm Thomas Telekti, sitting at the DHI office in Vienna. Today's agenda is quite short. If you look just at the agenda, a short overview about auto-calibration, then a practical example for a calibration using time series, and then one for steady state calibration. That's it for today. Let's start with the short overview about auto calibration. The first challenge is to activate it. So you have to go into the model type, right at the top of the setup tree, and you have to activate the auto calibration. Only then the special analysis bullet point in the tree will open, and you'll have this auto calibration entry here. And if you click, it opens up the auto calibration editor. The three editors we'll use today is measurement station, plots and statistics, and auto calibration, among others, of course. The editor here at the bottom again is split into several tabs. The first one is about the methods, and I personally didn't play around with all the parameters. I guess if you are new to auto calibration, you won't either. This is probably more something for specialists. Then we have 4 tabs with parameters to calibrate. I'll talk about them in a second. Then we have the targets, locations with measured pressure or flow, maybe constant or a time series. And finally, outputs with the best parameters and the results in all locations. And now let's have a closer look at these parameters to calibrate. The 4 pipe frictions, which adjust roughness values. You'll see that because we used that today. Then there is the option to calibrate node demands. And what they really do is the routine scales patterns up and down. So if you have connected patterns to your demands, if you only have one, all node demands will become larger and smaller. If you have several, well, then you can choose which patterns to scale. We can also use links, open and close them, either pipes or type of valve. And finally, adjusting leaks is also possible. This affects junctions, and it adjusts the emitter coefficient of these junctions. Today, we'll use pipe frictions only. Of course, you can combine those. Possibly perhaps it's a bit more challenging for the engine to find a solution, but in principle, you can combine those targets or those methods. So we start with the calibration of a time series. It's a very small setup with a tank here and a pump, a well. The tank has 400 cubic meters. The demand is over 1,000 cubic meters per day. So obviously the tank is not big enough and the pump will switch on and switch off. There is a daily demand pattern behind it. And we have one measurement station here for pressure. Yeah. So let's have a look into the model. Here it is. So let's start with the plots and statistics because actually, let's start with activating auto-calibration, as I've told you. So we have to activate auto-calibration, and here are the special analysis, and this opens the editor. We have one measurement station already defined. It's called P1 because it's a pressure station. We don't have any plots and statistic yet. No, plots and statistic, they sort of pull in measured time series and combine them with modeled time series. I create a new plot. Let's plot P1. I connect it with the one measurement station, and I add a time series here in the dat format. So that's a time series of pressure measured over 3 days, and it's connected to junction 5, which is here. Before we go into auto-calibration, I want to run a normal simulation because it's always good to understand the system before we run any of these tools. So I would run a simple simulation. It's a 10 millimeters roughness. Well, all the pipes have 10 millimeters roughness. If I open the pipe editor, you see here roughness is 10 millimeters. So my first simulation run is simply extended period hydraulics over these 3 days. Everything is prepared like if you watch cooking TV. Okay, ran over these 3 days. And now let's have a look at the results. They have been loaded automatically. Perhaps we make a longitudinal profile from the tank into the well. And we add the hydraulic grade line. Oh, here it is. Node head. Okay, so the pump is currently running in the first time step. And then let's add time series of the time series plot of the, oh, sorry, that's the wrong one. Pump flow and in the tank water depth. So this is the pump flow, and that's the water level in the tank. So here, here, the pump is filling the tank. You see that the water level goes up until you reach the off level, and then pump stops and the water drains and, flows into the system. Here we have a quite high demand. So this is what's happening in the system. And now we want to match the measured time series in this single location. I close those two graphs. Well, we haven't seen how well the current simulation really matches the measured values. This is because we haven't added the result file yet. So this is our result file, and we want to see the pressure in junction 5. And you see the green line is the one with the modeled one. So it's quite close, but not perfect. Essentially, we can create a perfect result because it's not really this is a tutorial setup. It's not a real setup. So the measured time series is fake. Good. So now it's time to start with the autocalibration. We insert an autocalibration. I call it all pipes because we will work on all pipes. The autocalibration always relies on one existing simulation run and modifies the parameters. In the first tab, we can choose between two genetic algorithms. I just keep the first one. Again, this is for specialists here. We want to change pipe frictions. So I insert one group of pipe frictions. And with pipes, I always have to define which pipes do I target. I want to target all pipes, but we need a selection here, and there are no selections available yet. So I create a new selection. In this case, all pipes. Here is a context menu. That's the fastest way. New selection list. I call it all pipes. So this selection list contains all pipes. And we add this selection list. I'm quite generous with the minimum and maximum friction. And I would call that all pipes 0.1 to 10 millimeters. Yeah. Nothing with demands or leakage. Yeah, and now I have to find the target. And here I target pressure in a junction. This is junction 5. Pressure junction 5. If I have several of these targets, I could give them different weights, but well, usually you will only use the same weight, and now we have only one target anyway. And down here, that's an important button here. I can either use constant values, then I would enter the constant value, or I can use time series. And here, in order to get the time series, I reference the plot. So all it does, it goes to the plots and statistics, plot P1, and takes this time series as the target time series. Perhaps I call the simulation, I give it a different name. And I think we are ready to run. Let's see. It's always a bit dangerous with these live demonstrations. Well, looks good. The setup is, the setup says 300 sort of iterations or 300 steps. So that takes a bit of time. The best objective is some sort of, I don't really know what parameter it is, but the lower it is, the better is the match. And you'll see already that there isn't much happening anymore. Perhaps if we, in principle, we could already stop. Perhaps you could also change parameters, but well, anyway, it doesn't take that long. There we are. And then the log file also lists how well the measured value was met in all the time steps. But I think let's go into the middle. So what we see here, we have this group all pipes, and the optimum roughness here is 0.366 millimeters. And you see that the match is quite good. If you look at the outputs, we get exactly the same information, just in a more readable format. So group all pipes, ended up with 3.66, and here again are all time steps. Oops. Yeah. And the most obvious way to check the results would be, well, first of all, the engine has created a result file already, and it has the optimum roughness in it. So it's one with 3.66 millimeters. We could use this one, and you'll see in green, it aligns quite well. Switching pumps on and off depends on water levels. So if you model for a long time, this could become out of sync, even if that's not a big problem. But here the match is fine anyway. Going back to the auto-calibration, if we change to the pipe frictions, you'll see that this is the calibrated friction. And now we can choose which friction really to apply, because 0.366 looks a bit weird. I will probably change that to 0.4, because right now, I mean, the roughness in the table is still the original one, you know? So this was a temporary change of roughness. But if I now want to use the 0.4 millimeters, well, I go to auto calibration. I say apply all frictions. Yes, I want to do that. Really fine. If you look at the pipes, they are now 0.4. And I could do a next simulation, which I call simulation run 3 with 0.4 millimeters, and run that one, and I then compare it. It will look, yeah, almost the same. If you have questions, please post them. I don't see them yet. Yeah, I think that's it for the extended period simulation, or for calibration of time series. Of course, that was a very simple approach, only one measurement station, not more. But the workflow is pretty much the same if you have 5 or 10 of these time series. From my experience, sorry. No, I mean, this is about the auto calibration tool, not about how to calibrate models. So there's a lot to say about how to set up measuring campaigns and how to look at the data and the results, but that's not really the scope of today. I close. Yeah, this one. Extended period simulation and simulation of a week is especially interesting if you want to fetch the behavior of pumps and tanks in normal conditions. So you see whether the model performs well if you have controls and things like that. If you're just interested in, roughness, or whether your system is connected properly, you may also just use a snapshot simulation, a steady state simulation. And this is what I'm showing you right now. I'm just opening the other database, which is here, oops, here. And in the meantime, let's have a look at the, well, I mean, there were a few slides, but they more or less just repeat what we've seen. So this is more for a reference than for really, I've shown you in, oh no, there's one important slide actually. I nearly forgot. So calibration, plots and stations, how do they fit together? Well, the calibration target has an element ID. This was the junction ID 5 in our case, and a plot ID. The plot ID is the same as in plots and statistics. Why is that? Because in the plot ID, we also have the time series, as you have seen. And the time series is used to run the calibration. So this is the way how the time series come into the calibration editor. Measurement and stations are not really needed. I mean, they are good to understand the thing, but for the calibration itself, they are not needed. But they are needed for the plots and statistics. So how does this work? A measurement station can have several plots. And in the measurement station, there is also an element ID. It was actually the one this was responsible for, I can't see that right now. This was a line pointing from the orange dot to junction 5. And this element ID tells plots and statistics which element to plot, because the result file contains thousands of pressure graphs. But this element ID tells plots and statistics which one to plot. What is a bit sort of confusing is that this element ID and this element ID, they're not connected. I mean, they should be the same, but they are in different editors. I was a bit confused at the beginning. Okay, now we come to the steady state calibration. This is a modified setup from a real campaign we did. We have a tank with a constant water level, or more or less constant level. We have two outflows here, large outflows, and we have a few measured hydrants in that case. This was the measured time series, and what I mean with snapshot calibration is that we look just at this 10 minutes, more or less constant pressures. And we see that one gauge has 64 liters and the night minimum is 10 liters, and the difference must be 60. Yeah, it's not so important. What I want to show is we have measured time series, and we try to get some constant steady state conditions, and then we take the values here as steady state flows or pressures. The measurements are I've prepared a spreadsheet where I have all the gauges with a name, where their coordinates. This is the junction ID. This was the zero level of the pressure meter, and this is the resulting hydraulic rate line. And first of all, I want to import this external table into Mike Plus so that I can see the measurement stations. I go to the tools, import and export, load a predefined gauges to stations. I could import the flows as well. No, I want only to import the pressures. Well, seems to work. And run. Just an example how to live with, how to work with external data. So now I have my gauges here. I don't see the demand gauges, but those are the pressure gauges. What I didn't show you is that I have added two measurement stations. I have added two user-defined columns to the measurement stations. One is the one which just says it's a pressure gauge, and one says it's one is the measured value. Why is this invalid locate ID. Oh, because the junction is missing here. Junction is the first thing. I don't know why. Perhaps there was something wrong in my import nonetheless. I don't know. Junctions. Sorry. It's a bit awkward to do that this way, but that's part of live demonstrations. So something was wrong here somewhere. But that's a good thing about the live sort of checking, error checking. Okay, and as before, I start with a simulation of, in this case, of 1 millimeter, 0.1 millimeter, sorry. All the pipes have 0.1 millimeter to steady state simulation. So we run this one and look at the results. This has nothing to do with auto calibration, what I'm doing right now. This is just to show you the current situation. And one way of doing is to add the result layer with the hydraulic grade line, node head. Okay. And I've prepared symbology. Yeah. So you essentially see the modeled hydraulic grade line and the measured, and there is a difference, and it becomes even larger down there. In some locations, it's quite good. Well, still 3 meters difference here. So this is a way of looking at the map, and I think it's always good to look at the map. However, we can also pull the results out and put them into a spreadsheet. So here I have the table with the computed values and the measured values and the difference and the standard deviation. And here is a graph, and you see we are way out of any acceptable difference. I mean, it's 2 meters, 6 meters, 12 meters. Our model is way too high compared to the measured values. And the best way to look at these results is actually a map. Now, this map has been created in QGIS, and there is some scripting at the background to combine the measured and the modeled values in that way. But I think it's especially for this webinar, the best way to understand what's happening here. So we have the flows to the big outlets here. We have the gauges. This is the modeled value. This is the measured value, and that's the difference. And what you see is that here, the difference increases. So we have 10 meters difference. Here we are only 2 meters above the measured values. And the measured values sort of create a plane, and the modeled values create a plane. In the best case, those planes are the same planes. And here there's a difference. The fact that the difference increases here, so we are too high with the model, means that our roughnesses are probably too low. We have to lose more sort of energy level along the way. On the other hand, here you see that the differences are more or less the same, 2 to 5 to 7, 3 meters. But you'll also see that, I mean, there's no flow here. So the measured values here are more or less, yeah, plain, equal, and the same goes for the measured ones. They are just 2.5 meters higher. And if we succeed to pull the modeled values down here somewhere, probably all the other values will go down as well. Okay, so let's continue with the auto calibration in one pipe group. We open the auto calibration. Let me quickly check my notes. I think that's fine. So we start here they are, auto calibration. I insert a new calibration. I start with all pipes. That's pretty much the same approach as beforehand. I include one pipe friction group. I've already prepared the selections, so all pipes is already present. It goes from 0.1 to 10 millimeters. Yeah, and now I need these 10 pressure meters in the targets as well. Measurement stations are for visualization, but I now need them in the calibration editor. So I repeat my import. Hopefully this one works better. And now I want to import into the targets. So it's from the Excel spreadsheet to MW AutoCali targets and my assignments. Okay, looks good. And here they are. By the way, this auto calibration editor consists of several tables. I mean sorry. Yeah. Oh, here it is. So, no, come on. The first one is the methods, and this is the same. Those entries here correspond to the methods. The pipe frictions are a subtable because you can have several pipe frictions, and the same goes for node demands, subtable, closed lengths is a subtable, leaks. And also targets is a subtable. And I've imported into this subtable called Autocali targets. We'll publish probably these tutorials, and you can have a closer look at both the import and the data itself. Anyway, here we are. The ID, data type, location, and now we have a constant value, not a time series. And again, I think that's it. Yeah, I think that's it. Let's see. Yeah, so you see again, it starts with a very large number and then it decreases. And this is a genetic algorithm, so it creates some, I don't know how many different model setups and runs simulations and picks the best ones and combines them, and there's a next generation. So it's a way copied from nature to find a good solution. Apparently, it doesn't always find the optimum, so there might be a better one, but it's pretty fast. And we see that, well, I can look at the outputs here. We see that the result is 1.7 millimeters, and then the various differences here. I could try to create the map again, but it's not very easy to read. So I'll jump right into the slides where I've prepared already the spreadsheets and the ArcGIS results, so you can see what how well the auto calibration performed. So that's Autocalibration 1 pipe group. So here we are. So I've taken the outputs and pasted them into a spreadsheet. Again, you see the differences here. Apart from one, they are quite good. And here now you have model is higher than measured value, and blue model is lower than measured value. And the standard deviation is 0.8. I mean, generally speaking, this is really quite good. So this is how the whole thing looks directly in Mike Plus, and this is again a post-processing in QGIS. Purple means model is higher, blue means model is lower, and a small dot means only half a meter away, so already quite close, and this is more than half a meter away. So we see that in this region here, we are already quite good. I mean, I've told you that if we match the pressure here, or the grade line here, all the others will follow, more or less. So this is what happens. Yeah, and along here, well, here we are a bit too high, and here we are lower than the measured values. So here we are half a meter higher than measured. Here we are 2 meters lower, which means that we lose 2.5 meters too much. If we had here 0.65 meters difference, then both would be by the same value off, which means that the roughness is probably okay. Something else is probably not okay. Or even if both would be minus 194, then they would be on the same level. And again, they are both off, but the difference is the same. And the roughness in between is probably also correct. So it's already very good. I mean, but for the exercise, we still want to improve the result, and we want to use 2 different pipe materials. And if you look at the map of materials, you see cast iron here, cast iron there. Here in this section where we have disagreement, there is this one of these other materials. So why not split the auto calibration between cast iron and other materials? And this is what we do. So I could make a copy here of the auto calibration, but I simply material cast and other, just rename it. This is up to you how you want to do it. I want to keep the targets, but I insert 2 additional what's called control here. I would disable the old one, then it's not used. And then we say material cast iron. I've prepared the selection beforehand with all the cast iron pipes. And we had 0.7 as a result. So I would assume that if I split that up, cast iron is somewhere above. So let's say I gave from 1 to 10 millimeters. And material other. Again, we have already a selection here. And here, the minimum friction is 0.1, and I would say 2 millimeters. I mean, I could call that 0.1 to 2 millimeters to be more precise. And this one is 1 to 10 millimeters. For some reason, the editor complains that some of the pipes are selected in other pipe groups. True, but those two don't overlap. So I'm not 100% sure why. I think we should improve this error message for cases where those two pipe groups overlap. Yes, run. Looking at the time, yeah, we are almost finished. Yeah. You'll see that the best objective is slightly slower than it was before. I see some questions here. Okay, 5 questions. I think I can answer them in a minute. And you see that now the cast iron is quite high, so quite high, higher, 5.7, and the others are 0.6. So we had this split into these two directions, and the result should be better. Again, I'm just showing you how I did that. There is a report which contains the same thing, and then you can export the whole thing to Excel or to Word, and then you can post-process the data. We can't use the plots and statistics here because there is no plot if we don't only have a one-time step. So plots and statistic is not for any use in these steady state calibrations. And let's have a look at the final slides here. So this is the copy and pasted tabular result, and you see here we had 1.9. It looks much better. And if you look at the results here, yeah, we are almost everywhere yeah, below 1.5 meter difference, which I think is already pretty good. 1 meter would be 0.1 bar. Yeah, of course, perhaps there's something strange here. You could also define a single pipe as a group and let the algorithm find the real roughness here, and then you could investigate whether there's something wrong. I mean, if you get a roughness of 50, then possibly something is closed here, not only very rough. And this is in principle. Oh no, sorry. We can still apply all frictions to the database, and we should do that because it takes all active pipe frictions, not the inactive ones, and it applies the approved frictions. So if you go back to the model and we look at the pipe frictions, we have those two here, 0.6, well, 3.5, I would probably use 0.6. And for cast iron, 5.7. Oh, 6 is probably good enough. And apply all frictions means apply all active frictions. And if we open the pipe editor now, we'll see that we have 0.6 and 6 millimeters, depending on the material. I would thank you and announce some upcoming events. There is one in 2 weeks, validating models with the open source Python library model skill. It's a bit of an extended version of the webinar we had a couple of weeks ago, only focusing on model skill, which is, by the way, another tool to check the validity of models. So for calibration, but this is really for people who want to use Python and code. The examples are probably focused on marine projects, but in principle, they are applicable to networks as well. Unfortunately, we had to cancel the manhole losses webinar, which was planned for May. Yeah, hopefully we can reschedule it later that year. If you have any suggestions, please write to Evan. I would also like to draw your attention to the series of YouTube videos. The exploring new zone water balance tools for water distribution is from me, but I know that our colleagues in Australia or Asia are about to release 5 new videos. At least that's the plan. I don't know what about, but they've contacted me concerning such videos. Thank you for your patience. And if you enjoyed this webinar, please spread the word. Contact Evan for questions or suggestions for training in general. And if you have any questions specific to this webinar, contact me with this email address. And with that, I thank you very much. I wish you a good evening, good day, wherever you are. Goodbye.